Okay, we're going to spend a second day on section 2.2.2. If you did not turn in your assignment from day one, it was due last night at 11:59. Please do that today. It is question 52 and 53. So, and there was a Google slide deck that you needed to do two slides for, and it was yesterday's video. So you can still get partial credit and probably generous partial credit, right? There will be a point deduction, but I'm just more concerned about you keeping up with the assignments and developing your knowledge. So on to day two. So let's take a moment to just kind of review some of the ideas from yesterday. One of them is that whenever we have a situation where we see that our y-axis is labeled, here we have meters for this y-axis, and our x-axis is labeled, and we've got seconds down there. When we have that, all of a sudden the slope takes on significance. The slope in this case means something specific. In fact, because slope is the rise, right, rate in change, the change in y divided by the change in x, the run. Here we're looking at meters per second. So this is a speed. So when we look at portions of this graph, we know that it's communicating to us how fast something is going. And in fact, if I was to consider just this small portion of a graph, I know that if this was the race, they said go, on your mark it said go. Right here at the very beginning of the race, the person is 5 meters away from the starting line, and for 6 seconds they do absolutely nothing, right? You'll notice that their rate is not changing. They remain exactly 5 meters from the starting line the entire time. So in this case, we can see this is a slope of 0. My change in meters is 0. My change in seconds is 6, and 0 divided by 6 is indeed 0. So we're going at a speed of 0 meters per second. Now, if I was to be like the clown from yesterday and get flipped around, all of a sudden I'm not going towards the finish line, I'm going back towards the starting line. In fact, let's be specific. It's not just that these are meters, but more specifically, they're meters that you are from the starting line. So back here at the origin, you are 0 meters from the starting line. You're beginning the race there. And this person, right, didn't move for 6 seconds, and now they're going 3 meters toward the starting line in 1 second. So this has a negative slope. We're going backwards, so we would record this as negative 3 meters per 1 second, or negative 3 as a unit rate. We'd just say meters per second. So that would be part two. Part one was 0 meters per second, and then the second part is negative 3 meters per second. If something happens, I get turned around and I realize what's going on. Right now, you can see that now for the next bit of time, I'm traveling at a new rate. And in fact, if I try to pick a couple spots on here where it looks like I can estimate this, it looks like this is a decent spot and this isn't bad. So if I was to look at my change in y, I can see that y is changing by 1, 2, 3, 4 units, and x is changing by a single unit. So here I have a speed of 4 meters traveled in 1 second. So my speed is just simply 4 meters per second, And then the other thing that we were reading from this is we were told if the race was 20 meters long. So what that means is this is the line, it's dashed, but this is the line y is equal to 20. Y is equal to 20. And if you'll notice, it's not changing, right? Y is always equal to 20 as I move along there. Time is changing, but it's kind of like, hey, have you ever noticed that when you've got a race going on, the finish line doesn't move from the starting line? The finish line is always the same distance. That'd be an interesting race, but in normal races, some hypothetical one I'm going to stop thinking about, but in normal races, the distance from the starting line doesn't change. So you have to travel these 20 meters in order to finish this race. So this person's race can be described as 3 distinct chunks, and we're going to talk about that in one of the problems today. We have a way of writing something called piecewise functions, and piecewise functions allow me to break up a situation into different chunks, and I'll share with you a notation that we commonly use to do that. Let's just take a quick look at some of the answers from yesterday. So this was from Heat 2, and we had someone named K, and K's race was graphed by the equation f of x equals 2/3 x plus 1. What was her speed in meters per second? Well, at this point, we're starting to recognize that speed is right here, right? It's the coefficient of x, and she's traveling at a speed of 2 meters per 3 seconds, 2 meters per 3 seconds. But if I was going to do meters per second, I could look at this as a decimal and say her speed was 0.66 repeating meters per second, or approximately 0.67 meters per second. And it also says, did she get a head start? And the answer is yes, right? You can see right here there's a 1 meter head start, because at the beginning of the race, when t is 0, this person is 1 meter away from the starting line. Elizabeth's race is given by the equation 12/16 x plus 4. Who is riding faster? Well, if I take 12/16 and I reduce it, I do notice that that has a common factor of 4. And if I divide 12 by 4, I get 3. If I divide 16 by 4, I get 4, right? So it reduces to 3/4, up 3 over 4. But also expressed as a unit rate, it's 0.75. And then these are again meters per second travel. So I can see, because 0.75 is larger than 0.66, I know that Elizabeth is traveling faster. And how do I know that? I know that because I'm looking at the coefficient of x, and because Elizabeth has a larger coefficient of x, she's multiplying by 0.75 every single meter, every single second. She's going about 3/4 or 0.75 meters away. Another nice opportunity to think about multiple representation is we were given Hannah's race as just a table of values. So she started pedaling, her shoelaces came untied. Being careful not to get her shoelace tangled in the pedal, she rode slowly. Hannah's race is represented in the table below. At what unit rate was she riding? So here it doesn't matter if we're being told that she's riding at a constant rate, right? This is not, she's not accelerating, but we're told these are all constant speeds. I need to just pick two of these values, and it doesn't matter which one. Just pick two of them and then calculate the slope. So I could, for example, pick these two values. So you can see I've got an x and a y and these two values. And we just remind ourselves that the I need to figure out delta y, and I need to figure out the change in my x values. And of course, the slope ratio would be that change in the y, change in distance in the case, divided by the change in time. And that will give me, so if I look at this 18, I'm just going to go these numbers minus this. 18 minus 10, 18 minus 10 is 8, over 42 minus 14, and I'm embarrassed to say that I actually just typed that into a calculator. 42 minus 14 is 28. So I have 8 over 28. And if I take that fraction, 8 over 28, I can reduce it. It has a common factor. It ends up being 2/7. So this is the same as 2/7. But I want to point out that it doesn't matter which one of these ones I pick. I could pick different ones. So for example, let's say that I picked this point and the first one again, right? Let's say that I use the 14 and the 10. Well, in this case, my change in y for those ones I've circled in green would be 14 minus 10. So I'd have a numerator of 4. And my delta x would be 28 minus 14. And guess what? I could even do that. 28 minus 14 is 14. And if I reduce that, both are divisible by 2. I get 2/7. So you can see if we're traveling at the same speed, if we're looking at a linear relationship, it doesn't matter which pair of points we select and calculate the slope, we're going to get the same thing. I'm not going to do it for a third pair, but the third pair that I haven't considered would be the 42 and the 28, and the 18 and the 14. But you guessed it, if I was to calculate the slope there, it would be the same as well. So clowns will be clowns, and we've got a clown here. And this clown is just doing the wonderfully funny thing of traveling backwards. So you'll notice at time 0, and sometimes it's nice if you see this and you think, hey, I'm not sure what's going on just by looking at the equation yet. That's okay. Look at a different representation and it may help. So remember, x was time in seconds and y was distance from the starting line. And if I consider time 0, that's the start of the race, if I put 0 in for x, this becomes 20 minus 0, which is 20. Oh, and at 1 second, the clown is at 19, right? At 2 seconds, the clown is at 18. So what's happening is the clown, of course, is traveling backwards. It's coming from the starting line back to the finish line. All right, so this is one of 2 questions that I would like for you to do today. This question, I don't think I'm going to say much here. I want you to think through what's being asked and go ahead and write responses for both 54 and you're going to do 55 in your composition notebook. 54 and 55 will be starred notes. So these will be the things that I asked to see that you have down in your notes and you've got completed. So this is 54. You can look at it in the book or you can read it here. Let's go on to 55. So this is question 55, and unfortunately it's related to an activity that we were unable to do in classes here. So instead, I'm just going to go ahead and talk about piecewise functions and describe the notation that we use for recording them. So when I look at this function, and I would say certainly this is a function because at no point do I see an x value having multiple y values. It occurs to me that I can't describe this with a single equation because this function over the course of the domain from x is 0 to x is 9, three different behaviors are observed. And what we do is we just basically describe the 3 different behaviors using 3 different equations. So if I was going to say that this is the function f of x, right, I could break up f of x into 3 pieces, and this is how it would look notationally. F of x is equal to, well, it depends, right? It depends. You can see for part of it, in fact, from 0 to 4, one thing is happening, and I can write here from 0 to 4, and this is that's interesting. It actually, because there's no discontinuity here, I don't have to worry about the function jumping. So I could say it could be equal to 4 here too. It doesn't matter. But I think what I'm going to do instead is below I'm going to say for the second behavior from the spot 4 to 6. So you can see I'm breaking it up into this chunk of time. That's one behavior. And then this little chunk of time. And then this little chunk of time up to 9. So for that last chunk of time, I'm going to pick up 6 and I'm going to include this spot. So the 6 and then going up to, and I'll include it on this end, the 0.9. So there's 3 different things happening from 0 to 4, one thing's happening, from 4 to 6, one thing's happening, and from 6 to 9, a third thing's happening. And what are those things? Well, if I just look at this first chunk, I can see I've got a y-intercept at 5 and a slope pattern of decreasing by 1 and going over 1, 2, 3, 4. So I can write the equation of that part. That equation is, I'll just say y equals negative 1/4 x and then plus 5. I didn't quite leave enough room there. I should have spaced that out better. Oh, Mr. Roberts, I'll try and recover this. I'm going to kick this over a little bit here and give myself some more room. So now I can write, and I'll just go ahead and use y. Y is equal to negative 1 over 4x, and then I'll just say plus the number 5. So that's one behavior. The next behavior is interesting. This is just y is always equal to 4. So if you look at it for this section right here, it is not going It's the distance is not changing at all, right? The entire time the distance is 4. So from 4 to 6, the function that governs that portion of this piecewise function is just y is equal to 4. And then for the final portion, I know the slope is up. The slope is up 1, 2, 3, 4, 5, and then over 1, 2, 3. So I know it starts with y is equal to positive up 5 over 3, 5 thirds x plus, and I'm actually going to leave this blank right now. I'm going to leave this blank, and I'm going to leave this to you to think about, how in the world could I figure out that y-intercept? I mean, I can imagine that the y-intercept somewhere down here. In fact, it's probably negative. But I think if you look at this perhaps on a bigger grid, you can manage to figure out where that's going to be hitting. So more about that next week. We'll talk about how you can find the y-intercept if it's difficult for you to extend a graph and look at it. But that's it. We're at about 16 minutes. We'll stop there today. So again, 54 and 55 are starred notes I want to see. If you have not finished 2.2.2, please submit that today, and you can still receive credit, partial credit. There'll be a small point deduction. This is Mr. Roberts. Have a great day.